All right, here we go. Let's talk about the turn-off and turn-on characteristics of a PN diode in a large signal response. So, in the last segment, we had developed this charge control model here, which just looks, in a sense, in the integral charge that is sitting as the number of minority carriers on the, say, P side, minority electrons on the P side, and they take some time to respond, and they result in a change in the voltage and the current that looks at first a little bit strange. And we're going to figure out what is the storage time here, which is the turn-off characteristics, and also the recovery time. And we'll do that in the next few slides. Okay, so here's the circuit again that we're looking at. We started out from the charge being piled up in the diode in the forward bias direction, and then at time t equals 0 we're going to flip this switch around and see what happens to the device. The question now is, why is the voltage remaining constant and the current is changing instantaneously and maintains a certain current throughout a certain storage time? Let's figure that out. Okay, so for a capacitor, the voltage cannot change instantly. So we cannot change the charge instantly. So let's get the boundary condition for the charge. So the assumption is that we've charged this diode up for a long time, and we are in steady state up to time equal 0 minus, and there is no change in that charge anymore. So we're fully charged. So therefore, we can figure out what is the charge in the system, in the diode, and it's at time just before the switching, it's I forward, the forward current flowing in this direction, times the minority carrier lifetime. Okay? So that's the boundary condition. But we haven't really said yet why the voltage remains constant and the current can switch. So that is really now the condition we need to examine a little bit further. So we have switched the circuit to the switch to go this direction. And we have a voltage that we apply from here to here, and let's sketch it like this as a vector. And now we need to sum these voltages up across the device. So we're going to have a voltage here and a voltage here with the resistance of the diode, okay? All right, so we know that actually the voltage we had applied here is exactly opposite of what we had originally. So let me call this as a minus V of time 0, okay? That means in order for this voltage to have switched, that means that the current that is flowing here has to balance these voltages, okay? So R needs to balance this out, okay? So the current must be generated by this diode. And the question is, how long can it take for the diode to supply this voltage, and how fast will eventually this voltage decay? So let's do this calculation. So the way to think about it is this way. You have this charge in the minority carrier region, and it's an integral charge. And now we're flipping the switch. And we know that we want to calculate this charge control expression here for times greater than 0. So that's our differential equation that we want to solve. And Q is the charge is a conserved quantity, meaning we destroy it by minority diffusion, but it has some continuity to it that we have like a state variable, okay? So we use charge here as a state variable. We're going to plug in that the reverse current here is approximately constant for the time that we evaluate this expression. and we're trying to get to the storage time. We're trying to figure out how long this storage time can be. So we need to integrate in time from time to time equals 0 to the storage time, this expression of the differential equation. All right, and that we do this. We've done this before. You have an integral to solve like this, and you come to a log-based expression that we had done before. Okay, so nothing really novel here. We have, and we can solve this for the storage time. Okay? Okay. So here's this expression as a function of initial charge. And then we're assuming that at some point, at the storage time, the charge that is stored in the capacitor, in the diode, is going to 0. So we're going to cancel out this term in this expression, and that will make up the time segment at which time Ts has occurred. That's, in a sense, our boundary condition that we apply. All right. So that means we now have an expression for the storage time, which is really IR plus IF over IR in the log. Okay, and then the minority carrier lifetime enters like this. Okay? So, if you want fast switching in a diode like this, maybe you need it for switching, what you need to do is shorten tau for a very fast response. So scattering can be a good thing sometimes. Okay? It depends on the application that you're interested in. We often think of the minority carrier lifetime scattering being a bad thing, but if you want to switch this kind of device rapidly, it couldn't be a good thing. Okay, so now we have an expression for the charge here as a function of time, and we can solve it like this, and that allows us to calculate also the voltage that is on the diode as a function of time, and we see it here, the time evolution as a function of time in here, and therefore we have we can calculate in this charge control model the evolution of the voltage that is dropping over this diode. Okay. All right. So for the recovery time, the calculation is significantly more complicated, and I'm not going to show that in this course. The final result is given here with an error function. An error function looks like this. And you might recognize that the error function as a square root looks like this. And the original error function has the minus t squared in it as an exponential. So it's a Gaussian integral in a sense. But the point is, you might recognize this complex exponential in time and the square root behavior that might show up in the recovery time. As you evaluate those things numerically, the error function is somewhat of a pain. It's tabulated. There's an approximate expression that you might find useful as well. All right. So you can look up recovery times. You can look up expressions that are approximate for different lengths. So if your device length is much shorter than the diffusion length, you have an expression. And if the device length is much larger than the diffusion length, then you have a slightly different expression. But they all go as a function of the forward and the reverse current that is in the device. Okay, so it depends on the biasing of the device. The recovery time is not quite a linear expression. All right, so we're not going to go into more detail than that. We have an expression for the turn off and now we're going to look at briefly the turn on of this device. All right, so we have fully discharged, so to speak, the forward bias direction. We are now sitting in the reverse bias, and we're wanting to flip the the polarity on the applied voltage of the overall system again. Okay, so again we have the charge control model, and let's assume that we have fully charged this diode. Okay, we've fully charged the capacitive elements of this diode in the reverse direction. Okay, so we have a boundary condition for that. The boundary condition at the end is when we're fully charged, that again we have a forward bias current that gives us the charge that we want to reach. Okay, so the final charge we want to reach will be looking something like this, right? That we are inducing into the device again, and it'll grow in time like this. Okay, so there will be no minority carriers, and we're beginning to inject them in time. And now we're calculating the time it takes for that charge to build up, okay, in the charge control model. Again, we have the expression of the charge control model. We have a current of I forward in the system and the time relaxation time in the system for the overall charge. We have a differential expression for Q of t. Okay, so nothing really exciting here. At the end, we reach the final charge, and it's driven by the minority carrier lifetime. Okay, and from there, of course, we can calculate this distribution again. We can check that the boundary conditions make sense. So as we switch, there is no charge because we were in reverse bias, and this makes sense. All right, so this was pretty rapid on the turn-on. Again, the idea was you start from 0 minority carriers and build up the final minority carriers through this differential expression, and you see the time, the control charge grow in time up to the final point of supporting of being fully charged by a forward current. Okay. Now, let's look at the next segment on how we can rederive the steady state expression for the diode characteristics in the charge control model. So we'll do that in the next segment. See you then.